Hello viewers, you're welcome to my YouTube channel. This is our X channel, and today we'll be looking at a very fascinating topic, which is the limits of a function as it approaches infinity. So there are key things we need to know before we start evaluating a function as if input variable approaches infinity. One of those things to know is that infinity is not a number, but a concept. Infinity is not a number, but a concept. So because infinity is not a number, but a concept, that's why we cannot perform operations on infinity for this level, especially to say something like infinity minus infinity. We cannot do this. This is actually indeterminate. But you can say that 2 minus 2 is equal to 0. So why will infinity minus infinity not equal to 0? If a number subtracts itself, then it should give us 0. But for the case of infinity, it is different, right? And so the same thing, you cannot do this, infinity divided by infinity, because infinity is not a number, but a concept. So when we talk about the concept of infinity, we are actually saying that our input variable is growing larger and larger and larger. So that's one of the things we need to know about infinity. Next is to say that infinity has size. Infinity has sizes. It has sizes. Some infinity are bigger than others, right? For example, the set of the natural numbers and the set of the real numbers, right? So the cardinality of this set is smaller than the cardinality of this set. As a matter of fact, the set of natural numbers is actually a subset. It's a subset of the set of real numbers. Yes, the cardinality of the natural numbers is called the LF0. LF0. George Cantor gave us a whole lot of information about that. And then this is the infinity continuum. The infinity continuum. So the set here is actually less than this set. Although the elements here is infinity, but it's a countable infinity. You can count, right? But this you cannot count. And it's infinity. So infinity has sizes, right? And then lastly, we can attain infinity. Yes, in mathematics, we can attain infinity. We can attain infinity. We can attain infinity. We can attain infinity mathematically. We can attain infinity. So we can perform infinite sets of operation, infinite summations, and still get a value and still get a fixed value for it. For example, this is equal to 1. So this is us performing infinite operation, right? And getting a fixed number. These two, the set of all natural numbers. The set of all natural numbers, if we add the set of all natural numbers, according to Ramanujan, we are going to get -1 over infinity. Although this is a little bit advanced, right? This is not a normal summation anyways, but then this is by intuition. But what I'm saying in essence is that we can actually attain infinity mathematically, right? So with the understanding of these concepts, with the understanding of these things, we can now dive to evaluate limits of a function as it approaches infinity. Now let's do the following operations. So let's see how it works. How can I evaluate the limit of a function as it approaches infinity? So we will look at limits as x approaches infinity. X raised to the power of 4 plus x 3x squared plus 1, all divided by x raised to the power of 2 plus 8x plus 7. Number 2, the limit as x approaches infinity, x raised to the power of 6 divided by k plus 12x plus 5 divided by x raised to the power of 10 plus 2x. And then number 3, the limit as x approaches infinity, 13x squared plus 8x plus 1 divided by 6x squared plus 20x plus 50. And number 4, the limit as x approaches infinity, 2x raised to the power of 4 minus 3x plus 1. And then lastly, the limit as x approaches infinity for 2 raised to the power of x all over x squared. 2 raised to the power of x all over x squared. So let's see how we are going to evaluate this limit. Question number 1, number 2, number 3 is evaluated in a similar way. So I'm only going to evaluate question number 1, and I will give you the shots to do 2 and 3. So for question number 1, we can actually test by plugging infinity for the value of x, and we'll get infinity raised to the power of infinity is infinity plus 3 infinity squared is infinity plus 1 divided by infinity squared infinity plus 8 times infinity is still infinity plus 7. So infinity plus infinity is infinity plus 1 is still infinity, all divided by infinity plus 7 is still infinity. Now we don't know what that means. That's actually one of the forms of indeterminates, right? So but with this should have a solution. Let's see the right way, the traditional way of going to do this. Okay, so the key to evaluating this function, this is a rational function. When we have a rational function, I want to evaluate the limit of that function as it approaches infinity. What to do is to actually, we only care about the power of the highest denominator. What is the highest denominator? So for question number 1, the highest denominator here is x squared. So what are we going to do? We are going to divide each term with x squared, right? And if we do that, this will be x squared plus 3x squared. If we divide by x squared, you get only 3 plus, if you divide with x squared, you get 1 over x squared, all divided by, if you divide with x squared here, you get 1 plus, if you divide with x squared here, you get 8 all over x plus, if you divide with, you get 7 over x squared. So after doing the division, the next thing to do is to plug in the value of x. So if you plug in the value of x, which is infinity, so x squared, which is so it's going to be infinity squared, right? Infinity squared is still infinity. So you have infinity plus 3 plus 1 over infinity. Anytime you have k, a constant dividing with infinity, the value or the answer is equal to 0. For example, 10 divided by infinity is 0. 100 divided by infinity is 0. 1 million divided by infinity is still 0, right? So 1 divided by infinity here is 0. Divided by 1 plus 8 divided by infinity, which is our x, is 0. Plus 7 divided by infinity is 0, right? So what we are going to have is infinity plus 3 is infinity. This is equal to infinity divided by 1 plus 0, this is 1, which is actually equal to infinity. So we are saying that as the value of x approaches infinity, this function grows larger and larger. It becomes unbounded, right? So this is what we are saying. Remember, this is not a value, it's a concept. It tells us the behavior of this function. How does this function behave when x approaches infinity? This is how it behaves. It goes larger and larger, right? Okay, so now let's look at something. The highest power of the denominator here is 2, and the highest power of the numerator here is 4. So when we want to evaluate the limit of a function and the highest power of the denominator, let me rub this off, and the highest power of the denominator, the numerator and the denominator. So if the power of the numerator is less than the power of the denominator, if the power of the numerator is less than the power of the denominator, but the particular case that we had there is, this particular case is the case where the numerator is greater than the denominator. So if the numerator power is greater than that of the denominator, then our answer will be infinity. For this, what case is this? The denominator is greater than the numerator. Denominator is greater than the numerator. Denominator is greater than the numerator. So this is this case where the numerator is less than the denominator, or denominator is greater than the numerator. So in a case like this, our answer will be equal to 0. Yes, when the denominator is greater than the numerator. When the denominator is greater than the numerator, then our answer will be 0. And lastly, for this case, the highest power of the denominator is equal to 2. Highest power of the numerator is equal to 2. So the last case, when n, the power of n is equal to the power of d, what's going to be our answer? Our answer is going to be the coefficient. Answer is the coefficient of the highest power of the numerator and the highest power of the denominator. The coefficients of the highest power of the numerator and the highest power of the denominator. So the coefficient of x squared here is 13 and the coefficient of x squared here is 6. So our answer for this particular case is going to be 13 over 6. 13 over 6. So when you perform this operation, question number 2 and question number 3, with the same method I did, the algebraic form, you will still arrive at the same answer, 13 over 6. And here you will also arrive at 0. So I'm going to solve question number 4 and question number 5 for us very quickly. Very quickly. Okay, so we are looking at question number 4. The limit as x approaches infinity for 2x to the power of 4 minus 3x plus 1. If you substitute x for infinity, then this is going to be infinity minus infinity plus 1. Of course, plus 1, since it's a constant, this is two big people fighting. Plus 1 actually does not have a play here. It does not have a say here. So it means like you're dealing with only infinity minus infinity. Remember what we said about this, an indeterminate. So what's the key to doing this? What's the key? What's the secret to doing this? The secret to doing this is that you're going to factorize out the highest power of x. Going to make a factor of the highest power of x. And so this will become the limit. The highest power of x here is 4. So this is the limit of x approaches infinity. X is to the power of 4 into 2 minus 3 over x cubed plus 1 over x is to the power of 4. Now that you factor out the highest power of x, you can now what? Evaluate. So for x, you put infinity. And this is going to be, of course, you have your infinity outside here. 2 minus 3 over infinity is 0. 1 over infinity is still 0. Right? So 2 minus 0 plus 0 is 2. So infinity times 2, which is still infinity. So this tells us the behavior of this function as x approaches infinity. But that does not mean that the value of the function will always approach infinity or will always be infinity if x approaches infinity. That does not mean. Of course, I showed you for this particular case the answer is 0, and for this particular case the answer is 13 over 6. It does not mean always infinity. But this is the cheat, the secret to dealing with something like this. And lastly, our question number 5, which is the most interesting for this lesson. Question number 5 is the most interesting for this lesson. So we'll be looking at how to evaluate the limit. the limit as x approaches infinity, 2 raised to the power of x divided by x squared. Divided by x squared. Okay, so for this, I'm going to leave us with a cheat, although I'm going to solve it later on with the traditional method, which is going to be by L'Hopital rule. So this, I have the set of function x factorial dot dot dot. I have 4 raised to the power of x, 3 raised to the power of x, then I have x raised to the power of 4, x cubed, then I have x log of x, then I have x, then I have log of x, and I have constants. Okay, so this tells us the rate. What you have here, it's very important that you note this. This here are different functions, but this is the rate at which these functions grow from the quickest to the slowest. From the quickest to the slowest. If you're dealing with a number and you use factorial, factorial grows faster than this, and this grows faster than this. This grows faster than this. This grows faster than this, and this grows faster than this. So this is the rate at which this function grow from the fastest to the slowest, right? So if you take for example, I'm dealing with this now. For example, let's say I'm dealing with this. So I'm using a number 2 raised to the power of 4, 2 raised to the power of 4, and then I'm saying 2 factorial. You see that this is bigger than this, but as I keep increasing the number, you see that this is actually growing faster than this is growing, right? So it's so important that you note this. It's so important that you note this, because this will help you to evaluate functions like this. You see that this function that we are dealing with now is a kind of function that we cannot simplify. We cannot simplify this function. There's no division you can do here. So this is the idea to this, right? So without solving this now, just with this cheat that I've laid for you now, you can tell me what's the answer to this question. Between this and this, which is bigger? Yes, 2 raised to the power of x, 2 raised to the power of x, 2 raised to the power of x is around here. This is 2 raised to the power of x. So 2 raised to the power of x is actually bigger than x squared. X squared is here. So this comes before this. So it means that this is bigger than this, grows faster than this grows, right? So it means, what did we say about when the numerator is greater than the denominator? It goes to infinity. So the answer to this question is actually infinity. How about I'm dealing with something that like this? How about I'm dealing with limit as x approaches infinity for x factorial divided by 2 raised to the power of x. X factorial comes before 2 raised to the power of x. And so if this be the case, then this will be infinity, because this is bigger, the numerator is bigger, this is bigger than this. If it is this, if the reverse is the case, then x factorial is bigger than 2 raised to the power of x, which is something here. So if the denominator is greater than the numerator, then I will be left with what? 0 as my answer, right? So this is a cheat for you to know how to solve question like this as x approaches infinity. But let's try to do it traditionally and see if we end up with infinity too. Let's try that. I hope you've taken note of this. It's so important. Let's try how to do it traditionally. Okay, so traditionally, of course, if I plug infinity here, I'll get 2 raised to the power of infinity, which is infinity, divided by infinity squared, which is still infinity. So this is an indeterminate form. So, but then there is a way to go about indeterminate form. We are going to differentiate using the L'Hopital rule. Using the L'Hopital rule. Using the L'Hopital rule. So this will become the limit as x approaches infinity. If I differentiate 2 raised to the power of x, what will I get? Remember, every time I differentiate a raised to the power of x, if I differentiate a raised to the power of x, then I will get a raised to the power of x ln a. So 2 raised to the power of x, the derivative of 2 raised to the power of x will give me what? 2 raised to the power of x ln 2 divided by, if I differentiate x squared, then I will get 2x, right? So this is ln 2 over 2 limit as x approaches infinity, 2 raised to the power of x over x. If I substitute the value of x now for infinity, I'll still get infinity over infinity. So that means I have to do it again. I have to differentiate again using the L'Hopital rule. So if I differentiate again, I'm going to have ln 2 over 2. Differentiating this now will give me the limit as x approaches infinity. This will be differentiation of this is 2 raised to the power of x ln 2 divided by, if I differentiate this, I'll get 1, right? I'll get just 1. So, which is needless of writing it. So this is what I'm just going to get. Now substitute x for infinity here. You get ln 2 divided by 2 times infinity, which is, this is a number, whatever you multiply with infinity apart from 0 times infinity. 0 times infinity is indeterminate. It's something that we don't actually know what's, it's surprising anyways why that does not have a particular value. But this is ln 2 divided by 2. If you multiply it with infinity, then you will get what? Infinity. So you see that this is actually true with what I did the previous time, right? So we've come to the end of this lesson. If you find this video interesting, don't forget to like, subscribe, so that when next video is uploaded, you get to see our video. Thank you.